Hey folks, in this video we're going to kind of continue with the previous ones, but now we're going to discharge the capacitor. So let me kind of explain my two pictures here. This is when we were charging the capacitor. We closed the switch, we charged it up. The charges ended up being this and this on the plates of that capacitor. When we were done charging that capacitor, the charge was capacitance times the battery voltage. So now what we're going to do is once that capacitor is fully charged, we're going to open the switch, remove the battery. So take the battery out of it, hook up the wires. That's this here. And then we're going to close the switch. So now we're discharging the capacitor. So, it's like as if you had a capacitor charged up, like a taser, for instance, is basically a glorified capacitor, or the bulb, the capacitor that makes a flash bulb work on your camera or on even your cell phone flash. Uses a small capacitor in this way. So you charge it up, and now we're going to close the switch and discharge it. And the first thing I want to talk about is, like we did when we were charging the capacitor, at 0 seconds, what's going to be the charge and the current? And after a long, long time, what's going to be the charge and the current? Okay, well, I'll start after a long, long time. So when you throw that switch, now again, we're pretending positives flow. Positives will flow this way, and they'll neutralize these charges over there, and eventually all the charge will be neutralized, and eventually the current will stop flowing. So after a long time, well, what do you have here? You just have a bunch of wire. So the charge will stop flowing and it'll be boring. At the very beginning, well, the charge was EC, as we had the fully charged capacitor. And what will the current be? Okay, well, at that point, this voltage, the voltage of the capacitor is the same as the voltage of the battery was. So the voltage was E and the resistance is R. So your current will be E over R. That'll be the magnitude of it. Now notice in the picture that current's going the other way. Okay, ignore that for a second when we actually do the math. Okay, so we're going to figure out charge and current as functions of time. So in between these times of 0 and infinity, we're still going to use Kirchhoff's loop rule. We're still going to go clockwise like we did previously. Now, in this case, when you go clockwise, you first encounter the capacitor, and you're going from the plus to the minus side. So that's a negative voltage of the capacitor. It's going to be negative, okay? And then you're going with what the current used to be through the resistor. So that's minus the voltage of the resistor. And that's going to all equal 0, okay? So this becomes negative Q over C minus IR equals 0, okay? And I'll recall that I is dq dt. So we got negative Q over C. I'm going to move this to the other side. So it becomes positive dq dt times R. So just like we did before, we're going to separate the variables. Now this time, it's a little easier to do. If I move my dt to the left side, it becomes negative dt. I'll move the R over there too, so you get an RC. On the right side, you get a dq over q. All right. So then we're going to integrate. So I'll make the left side the dq over q here. And the right side is negative dt over rc. Got to integrate that. Now time is going to go from 0 to some time later. What does the charge go from? Okay, so here's where people often mess this up. So normally people would say, oh, 0 to q, 0 to q, 0 to q there. Well, that's not the case. In this case, we started with q max. The starting value was q max. Okay, and then the final value is some charge that's going to be less than that. Okay, so that's our limits of integration. And if you don't do those proper limits, you will get a nonsense answer. Okay, so you have to think about what does a charge start off at? That's Q max. And I'll make that note of that. That's Q max right there. And what does the charge end up with? Well, it ends up with 0. Okay. All right, so then when we integrate this, you get the natural log of Q evaluated from Q max to Q at some other time later. And this equals simply negative d, or negative t, sorry, negative t over RC. When you do your log rules with this, you get natural log of Q over Q max. That equals negative T over RC. Then you want to integrate both, or you want to take the exponent of both sides. So to get rid of the natural log, so you get Q over Q max equals e to the negative T over RC. And you get your answer. You get Q as a function of time equals Q max, whatever that is, whatever the starting value was, e to the negative T over RC. Now remember, when we were charging this up, Q max equaled E, the battery voltage, times the capacitance. So that's our charge as a function of time. And does it follow this rule? So at 0 seconds, e to the 0 is 1. Q is equal to Q max. That's Q max. At e equals negative big time, e to the negative big number is 0. 0 times Q is 0. And our charge after a long time is 0. Okay. Now to find current, and by the way, recall that RC is equal to the time constant tau. So you could rewrite this Q as a function of time equals the starting charge, whatever that was, e to the negative T over tau. That's another way to write that. Now for current, okay, for current as a function of time, we're going to do the derivative of charge, dq dt. Okay, so you get Q max, and then you get the derivative of e to the negative T over RC is negative 1 over RC, e to the negative T over RC. And remember, Q max was equal to E times C, so if I plug that in, and then times negative 1 over RC, e to the negative T over RC, the C's drop out, and we get I, as a function of time, is equal to, there's a negative here, we'll talk about that in a second, E over R, and then our e to the negative T over RC. So that is our current as a function of time. Now, at 0 seconds, e to the 0 is 1, so this is negative E over R. So we had the magnitude of the current, right? Okay. After a long, long time, e to the negative big number is 0, so your current is 0, and that's what we get there. What's the negative about? Okay, well, that has a physical meaning. When you close this switch, when we were charging this up, current went clockwise. When you close this switch and discharge the capacitor, current's going to flow counterclockwise. This is why you get the negative there. So it's not an accident. The negative means the current's going to go the opposite way it did before. Okay. All right. So the next several examples, we're going to actually do examples that you might find in a problem. Again, for the next examples, if you have your packet, that'd be great. If not, you can copy the problems down. All right, hope that example is helpful, and thank you very much.